3 pi over 4, 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, and just reduce the fractions as needed. Okay? All right. Trust me, if you get that, that's going to save you so much grief. So much that I'm now going to talk about some other angles that are common that we need to know. Those are some of the main ones. Here are the others. What if I cut this first quadrant into 3 equal pieces? This would be 30 degrees, and this would be 60 degrees, this would be 0 degrees, and this would be 90 degrees. Do y'all agree with that? 30, double that, you get 60, triple that, you get 90, and then you keep going around, right? Let's go ahead and finish. Let's label this whole thing. It's going to suck. This is going to be in a little while known as our unit circle, all right? But I want you to understand where it's coming from. So what we're doing is we're cutting each quadrant into 3 equal pieces, right? Over here, we were cutting each quadrant into 2 equal pieces. 2, 2, 2, 2. Here we're doing 3, 3, 3, 3. And don't worry, we're not going to go 4, 4, 4, 4, or 5, 5. We're going to stop here, all right? So let's just keep going around and do all the angles in degrees. And to do that, aren't we just adding 30 each time? Right? So we're going to have 90. Let's see, this is 120, then 150, then 180, then 210, then 240, then 270, then 300, then 330, and then we get back over here, this is 360. It feels like I've been at this for a while today. Over here, when we did the pi over 4, weren't we able to do the whole thing? Like each one of these, we got them all, didn't we? Over here on this one, if we can start with this one right here, if we can figure out what this is in terms of pi, then we can count our way around. So let's look at pi is this half rotation, right? Like from here to here, we already know that this is pi, right? That's pi. Half rotation's pi, and we've cut that into how many pieces? This top piece, this top half is cut into 1, 2, 3, 4, 5, 6 equal pieces, yes? So this should be 1/6 of that pi. Pi over 6. Questions on why it's pi over 6?
So however many degrees you have from 0 to 180 is what you put pi over?
However many pieces we had, right, is what I put pi over here. So from 0 to 180, that's a full pi, right? From here to here is pi. And so since I'm cutting it in 1, 2, 3, 4, 5, 6 pieces, this is 1/6 of pi.
Yeah, that's right. Yeah.
Is that what you mean?
Yeah, like
Yeah.
however many pieces you cut it into.
It's pi over that. Mm-hmm. But that's not how I'm going to generate the rest of the angles. To generate the rest of the angles, I'm just going to count. So this is a single pi over 6 rotation, right? That's pi over 6. What would if I jump again? How many rotations have I, or how many pi over 6s have I done if I do it again? 2 of them, right? So this is the same as having 2 of those pi over 6s. Does that fraction reduce? 2 over 6 turns into pi over 3. So this is pi over 3. When we get up here, it better be what? It better be pi over 2, right? Well, let's just keep counting. This is pi over 6. This was 2 of them, right? This is how many of them? 3 pi over 6. But does that reduce? Yes, pi over 2. Okay? So everything's working out great. Now I'm on my what? 4th one. So this is 4 pi over 6, which is actually reduces to be 2 pi over 3. You have to keep track of where you are. 1, 2, 3, 4. I'm on my 5th one, right? So this is going to be 5 pi over 6, and that does not reduce. And then I get over here, how many now? 6, I'm on my 6. 6 pi over 6 is pi. Okay, next one, 7 pi over 6, which is not reducible, right? So I just leave it. Next one, 8 pi over 6. And then that reduces, right? 2 goes into both those, so 4 pi over 3. Where am I at? 8 pi over 6. This is 9 pi over 6. Does that reduce? Yes. It better be 3 pi over 2, right? So it is, right? 3 goes into both those. 3 pi over 2. I'm at the 9th one, so I have, what, 3 more? I get 10, 11, and 12. So 10 pi over 6, that does reduce to be 5 pi over 3. And now we're at 11 pi over 6, that does not reduce. And then finally, the very last one, 12 pi over 6, which is 2 pi. How many of you have seen these angles before, like before this class, but now you get like where they're kind of coming from? Has this been helpful at all to any of you? Yes? Okay. In my calculus classes, this is probably the one thing I show them, and they're like, what the fuck? You know, they get all pissed off because they never looked at it that way. They just looked at it more like, let me memorize all these angles. Count your way around, and then the memorization will come later. You'll just get so used to it. All right, that's it. Those are all the common angles. Those are all of the common angles that you should be familiar with in terms of, you know, the things we're going to use in this class. These are all the common ones. You should know them. These are all the multiples of 45 degrees, both in radians and in degrees. This is what it looks like. These are all the multiples of 30 degrees or pi over 6. You have to keep them separated initially when you're first learning them, because to get these you count a certain way, and then to get those you count something else. Later on we'll put them all together on one picture. All right, we still got time. Arc length. We're moving on. Arc length. So let's say that you have a circle, all right? It's a pretty good circle. And let's say that you go out, you know, it really doesn't even matter if this is a standard position or anything. Let's just say that you go out a distance r, okay? And then you rotate by some angle. And I'm saying positive rotation. Let's say we rotate, I'm just going to make it up. Let's make it go here, okay? Let's call that theta. Okay, so do you all see this positive angle in here? And then you see the radius from here to here is r. One thing that is very useful to us as human beings trying to calculate things is seeing if we can somehow figure out how long this is. We want to know how long this piece is right here. That's called the arc length of this. And we label it capital S. Now please do not confuse that with what I just drew a second ago when I said, hey, we're going to go out r, right? And then we're going to walk around by the same distance r and then draw that down, and I told you this is 1 radian, right? Notice in this, I was saying this is r and that's r. And then that's how we define 1 radian. Here I'm saying this is r, okay? And this is any angle. It's not 1 radian, it's just some angle. It could be 1 radian. What if it is 1 radian? What if I tell you this is 1 radian? Then what's S? It's r, right? But in general, whatever this angle is going to dictate the length of S. So I change it, S gets smaller, I make it bigger, S gets bigger. There is a relationship between all these, and here's what it is. S will always be equal to r times theta. That's the big formula. It's not even a complicated formula. It's a very simple formula. Your arc length S, okay, your arc length S is always equal to the radius times the angle. Always. If you want me to prove it again, let's have calculus class together. We can show that. That's Cal 2. That's Cal 2 as well. All right. So, one more thing about this formula that students will make mistakes on. This angle must be in radians. Must be in radians. For the formula to work, we have to be in radians to use the formula. All right, so I'm curious. Let's say I do this. Let's say I have some radius r. Okay, I go to here. And let's say I rotate this all the way around. All the way around here, okay? And I come back and I stop right there. Then S would be that whole distance around, wouldn't it? That's what S would be? Can somebody tell me what S would be in this case? 2 pi. You're saying because I went all the way around, right? I went all the way around. You're saying that this angle is 2 pi, right? So that S is going to be 2 pi times R. You didn't say R. That's what I want to make sure. Yeah, so it would be, I'm going to write it this way. R times the angle we turn through, which is 2 pi. And if I just rearrange that, 2 pi times R, do you recognize this formula? This is the formula for the what of a circle? Circumference, right? This is the circumference of a circle of radius R, which actually comes from this formula. So that's how we define circumference, right? This is the circumference of a circle. What's great about this formula is that it allows you to calculate the distance around a circle, and you don't even have to go all the way around. You can go to any portion of the circle and calculate that length. Let me give you another one. Let me give you a problem to work on here. Let's say that I have a dog that's chained up. That's illegal in San Antonio now. Do y'all know that? You can't chain your dog in your backyard. I so bad want to tell y'all a joke, but it's 2022 and I'm on camera, so I'm not going to. Let's say we have a dog. Here's my dog, D for dog. My dog is chained up to a post, okay? Let's make it a cow, okay? The cow's grazing. I've got the cow. No? Do you care? Dog, cow? Does it make you feel? So let's say that I have made it so that in some way this dog can only roam through here to here, all right? So this dog is leashed up. It can only go out that far. It can only swing through this angle. I'm going to tell you that angle is 18 degrees, all right? Poor dog. My question is, how much length, how much distance is this dog, how much distance can it swing out through? It's allowed to go back and forth here. I want to know how much length that is there. I need to give you one more thing. Let me tell you that the chain is 20 feet, all right? 20-foot chain. So I'm asking you, what's this distance that this dog can roam back and forth here? Well, isn't that the formula I just gave you? S equals R theta. Yes? That's our master formula. Do you know the radius of this in this situation? Yes, it's 20 feet, right? 20 feet here. So far, it's 20, right, feet, okay, times. Now, do you know the angle? Yes. 18 degrees, right? So times 18 degrees. So you just do 20 times 18? No, this is wrong, right? You cannot use degrees in this formula. It has to be in radians. It has to be in radians. Then you can use the formula. So the question now is, how do we convert degrees to radians? We haven't done that yet, have we? But I wanted to do this so you could see we need to be able to do this. So how do you convert degrees to radians and vice versa, back and forth? How do you go back and forth? Well, we do it the same way we did with the minutes and seconds thing. We need conversion factors, and we only need one. And I'm going to do it on this right here. Going back to the picture, if we do this rotation, that's 180 degrees, right? But that's equal to how many radians? Pi. That's our conversion factor, always. We know that pi is equal to 180 degrees. So when I'm over here in this problem, and I have 18 degrees, and I need to get it to radians first, all I'm going to do is write down 18 degrees, and I'm going to multiply it by something, right? And what I want is for my degrees to cancel, right? I want my degrees to go away. So over here, I need degrees on the bottom, and I need rads on the top, radians. So go to your conversion over here, right? This is pi radians is equal to 180 degrees. So what number goes where here? 180 goes on the bottom, right? And on top? Pi, okay? It's pi. Yes?
Do we put our calculators in radians?
You do not need to be in any mode on your calculator to do this. You don't need to worry about mode till we start talking about sine, cosine, tangent, and all that stuff. Right now, because here it's just numerical. The degrees are going to cancel, okay? And all we're doing numerically is taking 18, multiplying by pi, and dividing by 180, and that will be our answer in radians. So I would recommend you go ahead and just do that on your calculator and give me a decimal answer for that. Let's see. It's 0.3, right? 0.31415. So this turns out to be, yeah, I'll just put it here. This is 0.31415 radians. 18 degrees is 0.31415 radians. Did you all get that? Those of you who did it? Yeah. Okay. Now I can use the formula, right? Now I'm allowed to. So my S will be equal to 20. I'm not even going to put the feet. I don't really need it. 20 times 0.31415. And what is that? $6.28, right? Yeah. Is that what y'all got? 6.28, right?
I got 2.283.
Yeah, 283. I'm just going to round it 2 decimal places. 6.28 feet. Because, right, it was the length of this thing. Poor dog only gets 6 feet to roam at the end of the chain. Questions? I have another question now. Same situation, same poor dog. How much area does that dog have to roam in? I mean, I just gave you a formula, right, to figure out how long this side is. But wouldn't it be useful to know the area of this thing? Well, we have a formula for that as well. So I'm about to give that to you here. I'm going to start with a new picture. So let's say this is called area of a sector. We call this a sector. So if you start here, go out R, swing through some angle theta, you have this. We know how to measure this length, right? That length was S, capital S. But now we're more interested in finding the area of that. The area of that is 1/2 R squared theta. That's your formula for area of a sector. I'm not proving that formula to you. You're taking it on faith. Calculus, we prove it. Do you think that we have to be in radians to use this? Yep. Radians. Radians only. All right. Okay. All right, so let's take the dog on the chain, 20 feet, 18 degrees, and I wanted to know that area. So how much area is this right here? See, it's not a triangle. Do y'all agree? This is not a triangle. This is a sector. It looks like a pizza slice. It's got a curve at the end of it. So you can't use any formulas for triangles on this. According to that, the area is 1/2. Radius, do we know the radius? 20, right? And then squared, and then times the angle in radians, which we already did, right? It was 0.31415?
Yeah.
So this is times 0.31415. And so order of operations, square your 20 first, right? Square your 20 first, that gives you 400, divide that by 2. You get 200, multiply that times the 0.31415. I'm lost. 200, yeah. 62.83? $62.83 what? A measuring area, right? And this was 20 feet, right, for the length. So if we measure area, it should be the unit here, but what? Squared. So square feet. All right. How are we doing here? 10 minutes. Any questions? All right. We have 10 minutes. I'm not going to get into the next part, but we are going to still be here. So hold on. Don't tune me out completely yet. For your homework for this, do everything you can up until area of sector problems. Anything after that, just hold off. Submit what you have. Anything that I didn't cover today, just will be part of the next assignment. All right, just I'll let you go in and finish them later. I just don't want you to feel like you have to do something we haven't talked about. So we still need to do linear speed and angular speed. Okay, we haven't talked about that, which is really the most interesting part of this whole thing to me. It's like we're on the Earth right now, right? The Earth is rotating. Like, how fast are we going? Like, how fast are we moving around the center of the Earth right now? That's a linear speed. Yeah, it's really fast. We can't feel it, but we are moving, right? So do as much as you can over this holiday break for this section. All right. All right. So as you're starting to kind of wind it down, I wanted to talk to you about something else. I kind of like to mix in some random stuff, right? I've done that a few times already. So there's a mathematical problem that has yet to be solved that if somebody could figure this out would change the world completely. Everything we know about everything would be different, all right? So I'm going to try and explain it to you real quick because it's just a math problem. So if I give you any number, that number, like an integer, okay, nice whole number, every number is either prime or what we call a composite number. Prime means it's only divisible by itself and 1. Y'all are aware of the primes, right? Okay. Every other number other than prime is somehow the product of prime. So like 15 is the product of 3 and 5, right? And 3 and 5 are both prime. So this is called the prime factorization of that number. All right. So if I start at 15, I think we could all come up with 3 and 5, yes? All right. So for those of you who use phones? Yeah, we all use our phones, right? We expect that some of our information is encrypted, right? Excuse me. Encrypted, right? If we're doing a transaction on our bank or something, we are trusting that it's encrypted. It's not gonna, someone's gonna be able to hack into it, right? And there's different levels of encryption. Like some stuff you're like, okay, it's Snapchat, is it really encrypted? Probably not. If it's your bank, you really hope it is, right? There's different levels of security when it comes to encryption. The highest level of security is something called RSA encryption or some version of it. RSA encryption. It stands for the last names of the 3 guys who came up with the encryption method, all right? And it's a very simple idea. So here's how it goes. And I'm going to try and back up a little bit because you have to understand the history of encryption. I'm not going to go through the whole thing, but we all know that when we're trying to communicate with somebody else, go back historically, if you're trying to send a message to someone, there's always the chance that someone's going to intercept that message, right? Like if I want to tell you in the back, like, hey, do the homework, right? Or something, I'm give you some message. Everyone here is going to hear it, right? Unless I physically go over there and whisper it. But a lot of times, distance between us prevents us from being able to share a message. So if you have military troops on the front line, you're trying to send them a message, hey, withdraw, that message can get intercepted. It can ruin a lot of things, right? Are y'all familiar with the German code machine called the Enigma? If you ever watched that movie, what's that movie? About the guy trying to break the Enigma during World War II. Imitation Game, exactly. That's a really good movie. So, you know, the Germans were trying to hide messages. We couldn't break the code, all right? So there's been a history of this back and forth of I'm trying to hide my message from you, you're trying to get my message, right? This back and forth. Okay, until this came along. So the way this works is this. It's actually genius. Let's just take something simple. Let's say we take the alphabet A, B, C, D, E, F, right? And I want to make a code out of this. So I'm going to let A be 1, B be 2, and 3, and then 4, and then 5, and then 6. And then I'm going to send you a message, okay? And I'm going to say 414, right? So what does that message say? Dad, right? Okay, that is like the worst encryption ever, right? It's like, come on. It's a grade school encryption. But the actual idea is not that bad. I mean, what we're going to do is for every letter, we're going to assign it a number. So one thing I could do is I could say, all right, my first number is going to come off of this encryption. But my next number is a secondary encryption that I've created where now there's different assignments. So now 4 here means D for the first letter, but on the second letter I go off of a different key, so now this 1 actually is a B. Do you see that? And every single letter has a different sort of key. This is called polyalphanumeric or something like that, I forget. But you can imagine that if each one of these comes from a different sort of key, this could really get hard to break, right? Got the idea so far? All right, so I'm trying to send you a message, okay? So here's me strangling myself apparently, and here's you, right? And we're sitting here, and I want to send you a message. So I'm trying to send my message to you, all right? The message trying to go from here to here, and there's a bunch of people here that are listening, right? And they want to intercept my message. All right, so the way it works now, I still have time. The way it works currently is that if I try and yell my message, they're going to hear it, right? So what really happens is that you yell a message. And the message that you yell that everyone can hear is 15. You go, 15, That's called your public key. Everybody can hear it. Everyone sees it. All right? 15. And then I'm saying, well, I'm trying to send a message to that person. So I take the number 15. And what I do with that number 15 is I take my message, okay, and I use this number 15. I'm not going to go into the details of how I'm going to use this number. Just that, you know how I mixed up the letters? It has something to do with that. You use this number to encrypt. And then what happens is once you encrypt it, it's now kind of like that's a padlock. Now you've got this locked up. You've used this number to somehow scramble all this shit around. Now you've got this nice secret message, right? And what I do with this message, I yell it. So now I'm yelling my message that I wanted to send originally over. Now when I yell it, it's going to be like scrambled bullshit that no one understands, right? But these people can hear it, right? So you would think that all they have to do is say, hey, wait a minute, hold on. I'm just going to take that message that's scrambled and I'm going to use the 15 to unlock it. The problem is the only way to unlock this is to know that 15 actually comes from 3 times 5. That's the only way you can unlock the message, is to know that this 15 is 3 times 5. Which for us, I think we would know, right? In the real world, the number that's being yelled is not the number 15. It's actually 80 digits long, right? It's 80 digits long. It is the product of 2 prime numbers. So what we do is we have a 40-digit prime number, and we multiply it times a 40-digit prime number. These two multiplied together become your public key, and that's what you yell out to everybody. Here's my 80-digit public key. And then the person takes your 80-digit public key and they say, scramble it up, and then they send the scrambled message. And these people are like, we captured the message. The only way to break it is to know what these two 40-digit numbers were. And that is an extremely difficult thing to do. And it's simple in terms of 15 is 3 and 5, right? And you would think, okay, just put a computer on it, right? Let a computer go figure it out. Well, the standard, the guys that created this, the reason they chose 40-digit numbers is because, they said, look, if we go too small, like 15, people will break it, right? So we got to go big. How big do we go? The standard is this. Whatever this is, if every computer on the planet is trying to break this, it needs to take 10 times the age of the universe. That's the standard. That's the standard they use. So if computers get faster, what do? Go to bigger numbers. And the thing is, there's an infinite number of primes, so you're never going to run out of primes. We could do 80-digit and 80-digit primes and have a 160-digit number, and then your computer's just going to get bogged down. You're never going to break it. So when you hear about these things like, hey, they tried to get through the phone encryption and all this stuff, and they couldn't get in, I think in the back of a lot of people's minds, they